I think it's better to if there is a question during when I'm presenting, I think that's better because it's fresh in the mind and yeah.
Yes,
So
I would then forward it. So I will instruct the audience to post questions on the chat, and I will then interrupt you.
okay. Yeah, that's good.
Very good. So yeah, let's officially start this meetup today. I'm very happy to have Heikki Myllykoski, who is a PhD student in our group and works at the Finnish Meteorological Institute, to tell us about a very exciting application of machine learning, which is weather-based, weather radar-based impact nowcasting. And yes, so if you have questions during the talk, please post them on the chat, and I will forward them to Heikki. Yeah, thanks a lot, Heikki. Again, please take it away.
Yeah, thank you. So as said, I'm Heikki and I work at Finnish Meteorological Institute or Ilmatieteen laitos for people who are more familiar with the Finnish name. I work in our group here, Nowcasting and Intelligent Traffic Weather Research. And for my doctoral studies, Alex is my supervisor, and Seppo Pulkkinen, who also served as a project manager at the EDERA project here at the FMI side, is my advisor. So today I'm going to tell you about the EDERA project and especially the impact nowcasting related to it and my contributions through that to the project. All right, so this is the outline. First, I will go through some basic concepts like how do you do weather measurements and forecasting, and then for the presentations related topics like weather radars, nowcasting, and impact nowcasting, I will go a bit more into later, and then I will present the EDERA project in a broad sense, and finally the most and the rest of the presentation will learn with the machine learning that we did in the project. So here are some weather measurement instruments that I have gathered into these pictures. So first on the left, there is a weather radar. So inside that football, there is a parabolic disc that will send the microwaves to the sky and measure the echoes, and through that the precipitation. In the next slide, I will go a bit more further into the details of that measurement. Then in the middle, there is the on the left in the middle image, there is a rain gauge with the windshield, and on the right on the rack there is kind of like on the top of the rack there is snow depth sensor, and on the right there is a radio sound. So you would send this radio sound with a balloon to the sky, and it would give you information about temperature, humidity, and the wind speeds. And right on the bottom right, there is a METOP meteorological satellite. So these are just some instruments that's kind of like, they are not all of them, of course, and but they would give probably some idea to you what you would use to measure weather on top of your familiar thermometer outside your window. So weather radar. So here on the left again there is a weather radar. So inside the football, on top of it, or the radome, there is the antenna, and as you can see from the image on the right bottom side, there is kind of like the idea that it sends through the transmitter and the circulation the radio waves, and from the disk it will send then those to a certain direction towards scatterers in the sky, and then the echoes come back to the antenna, and the receiver will then obtain those, and then post-processing will produce this image here on the top. So the image here on the top is a reflectivity plan position indicator image. So it essentially is like when the radar shoots into some direction with some elevation angle, so angle with respect to the ground, and then it turns around 360 degrees, it will give this kind of image, and the radar will be here on the middle of the image. So yeah, then to combine these images, you will produce a composite, and these composites are kind of like can be nationwide or continent-wide if you have a lot of radars. And here on the right, you see like those 12 circles that represent the Finnish radar network. So there are 12 operational radars here in Finland. Then weather forecasting. So here are three like cases that are kind of like different time scales for different time scales and space scales. So first on the left top corner, there is the radar nowcast. So essentially nowcast is something that is usually from 0 to 6 hours to the future as a forecast, but usually these radar nowcasts are about two or so hours to the future. And then on the right, there is more familiar picture, maybe to most of the people. So this is just a weather forecast for 1 day or so, or at 8:30 1 day. So usually, like if you would want to decide what to do tomorrow, you would use this image, this map, rather than this nowcast, because these nowcasts are only for 2 hours and usually deal with certain measurements only. So in here it would be precipitation or rain. So precipitation equals rain in this presentation, and in meteorology discussion more or less it also contains hail as well. And then on the bottom here is an image from the European Center for Medium Range Weather Forecast, a model run by them, and it essentially shows certain like weather fields that I won't go too much into details, but it would kind of like be used to forecast the weather to 2 weeks into the future or so. Then here is an example nowcast from another project that we are kind of like working on, just to show you an image like that. Here is an European-wide composite, and we're moving these radar echoes in the image, the reflectivity field, different places, and we get a nowcast forecast from there. Nowcasting can be split into two kind of like paradigms. So the one that I showed you on the left here is a field-based nowcast. So we would have a weather field, or here in a reflectivity field, and then we would kind of move the whole field and predict based on that. Then in this presentation, more like present way to do nowcasting is this object-oriented storm cell nowcasting. So in this object-oriented way, we will take some objects from those fields possibly, and then try to predict or forecast the movement of those objects. So in this image, for example, we would have like here in the middle of it, there is a high reflectivity area, and then there is an ellipse fit on top of it that would be or nowcast, and I will discuss about this later on more. And another thing that is important to distinguish is that like this kind of like storm cell nowcasting most likely would make more sense to do when you're trying to nowcast convective precipitation instead of stratiform. So stratiform is kind of like precipitation that is more related to high pressure and low pressure systems and how those air masses interact, while the convective storms are more small and related to, for example, like if the ground is warm, the air will move upwards and will produce a thunderstorm in there. So for example, in Finland, we would have like these convective storms mostly during the summertime, but then like these stratiform storms are more kind of like significant maybe during the autumn season. Then to impact nowcasting. Impact nowcasting is kind of like about what the weather will cause, what the weather will do. So here I have 3 images essentially about lightnings, fallen trees through to a downburst probably, and then a flash flood on, I think this was somewhere in Australia. I took a picture from Wikipedia. So essentially like flood that happens quickly and would flood the roads. So usually when you model these kinds of things, you're interested on the hazard. So in these 3 cases, the hazard would be essentially the lightning, the flash flood, and the fallen trees. But then the exposure would be like how many people are there getting exposure from these events, and the vulnerability is like how significant this place is for this kind of hazard. And combining these, you would kind of get the risk for the like impact nowcasting. And again, like in nowcasting sense, we're talking about 0 to 2 hours into the future. Then the EDERA project. So EDERA project, the long name over there is Early Warning Demonstration of Pan-European Rainfall-Induced Impact Forecasts. And it was funded by EU, and one of the goals was kind of like to integrate some of these early warning products to this European Flood Awareness System, EFAS. And that's why we kind of produce these products for convective storms and heavy rain and flooding to help those civil protection authorities and hydrological agencies to possibly make better decisions when these kinds of events happen. This ran from the start of 2023 until the start of 2025, and my task in this project under supervision of Seppo Pulkkinen was to develop the ML model, the machine learning model for the convective storm hazard nowcasts or impact nowcasts, and then produce material for workshops where we ask from our possible end users what made sense to them and what did not. This was our consortium. So we had Spanish civil protection agencies and Spanish and Portuguese civil protection agencies, and on top of that we had some hydrometeorological agencies from Spain and Portugal, and also the European Center for Medium Range Weather Forecasts. Then on the side of the stakeholders who served as the end users and from whom we got the feedback from, the Syke, so the Finnish Environment Institute, Helsinki Rescue Department, Kymenlaakso Rescue Services, and North Karelia Rescue Department, as well as the Ministry of Interior from Finland, but there were of course others European-wide. So then to the machine learning model, or the model how we model these convective storms. So we essentially created this regression model to predict something called the hazard level of storm cells. And these hazard levels were estimated from data from European Severe Weather Database. I will go back to this soon enough. But the machine learning models that would predict this hazard level were obtained from scikit-learn, and the input features that were used were essentially, when we had those object-oriented storm cells, we took some raster field below it and took some maximum, minimum, and mean values from there and decided how to use those for prediction. And then the nowcasting part was made with this object-oriented manner. The models that we ended up using were extra trees models and neural networks, but more on those later. The data set of storm cells were obtained from reflectivity fields from the EDERA composite. So this is a European-wide composite, and they were from 2018 to 2022. First, when we were a bit still confused how we should do this. We had cross-validation, just a generic cross-validation on the training and validation set, but later we realized, okay, we should use time series cross-validation because when you have time-dependent variables, you should take those into account. So, for example, this radar network, they might change some settings later on, and new radars come to the data set or so to the composite year-on-year basis, possibly. So it's better to model the future with the data on the past rather than some of the future with some of the data of the past and some of the future. So we fixed that with the time series cross-validation later on. The test set was the year 2022, and we only used those months from May to September. And this was because the convective precipitation usually happens during these months, and we were more or less more interested in those. And then we have this reflective value of 35 dBz as a threshold. So essentially this dBz is something that the radar measures, and it can be directly translated to rain rate with certain functions. So this 35 dBz is about 5 millimeters per hour rain rate. Then for the demonstration, we had like data from August 2023 to October 2024. And then on top of these, we excluded nighttime because of the hazard level data set was affected by the nighttime variables. And then cell lifetime, we bounded to 30 minutes and the area for 50 minutes to filter out kind of like these clutter cells and also like 2 short-lived cells from the analysis. Then how we did the nowcasting with this object-oriented way. So on the left image, you see the storm cells and fitted ellipses. So first we took with OpenCV, we used this contour matching. We had the 35 dBz threshold, and we took those storm cells from there. Then we fit ellipses kind of like just, it was like kind of like hand wavy way, kind of like we took the PCA of the storm cell shape and then just slammed a Gaussian on top of it, and that was kind of like the ellipse that we got there. But either way, we had like these storm cells and we had their histories mapped because kind of like we had always the like measurement few moments before and the measurement few moments after this current image, and we could overlap those high reflectivity areas. And if there was enough overlap, then those cells were part of the same history. From the center points of the cells, we got the storm tracks, that is represented here with the red color, and then we used a Kalman filter to estimate how it would develop from there. And yeah, that's how we got our Nowcast. So like with time, the Nowcast kind of like is just the ellipse on, with the center point that is moved further with the Kalman filter model. Then for the machine learning model, we used these following features. So reflectivity, that was the thing that the radar measured. Hourly rainfall accumulation, so essentially how much in the past hour there has been rainfall. The convective available potential energy, so how much kind of like, it's kind of like this measure how much there is kind of potential for air to rise from the ground to like initiate convection, more or less. So it's kind of like I can't actually like give the exact definition. I don't know it that well, but either way, it's like this measure of how well there is like convection potential in that location. And then convective inhibition is like the opposite, so how much it is inhibited. Why the PCA plus fit? Why not do a Gaussian mixture model directly? I think over here the idea was to do just like really quick enough thing. So I'm not sure whether Gaussian mixture model would have taken any longer, but this was just kind of like we had like this earlier way of doing this, and we just took it there and like used it the way we did it. Gaussian mixture model would have probably been a really nice way to do it, but yeah, I guess like the idea is that we already had kind of just some idea how to do this with the PCA and with the like just slamming the Gaussian there. But yeah, it probably would have been a better way to do that like that, but not in this project.
There was also another question. What types of variables are related to nighttime?
So the nighttime variables I will go through soon. So it's more related to the variable that we will use to predict. So these variables over here are not related to nighttime yet. So it's the next slide. So, but over here, we had these raster fields that were to reflect the hourly rainfall accumulation, CAPE and SIN, and then there were the cell track attributes, which were like the area, age, and speed and direction. So this was the European Severe Database. This was our data set. So why the nighttime was so important is because these are kind of like observations made by people. So when people do an observation, they will send it to this European Severe Database, and somebody will check that, okay, this really happened. So some of these reports are made by people, not automatic instruments. And for that reason, because the people will be sleeping during the nighttime, we didn't include the nighttime. So only the times when people will notice. And this was kind of like, before we started modeling this, we realized, okay, this is something that we need to take into account. But yeah, either way, there are several weather kind of events that are severe weather reported in this European severe weather database, and they range from essentially, well, there is a long time or temporal domain from which you have these measurements, but these are all on European like region, and based on this we would do the estimation of these hazard levels. So we had the history of the storm cell, and we had the report at certain time and at certain location. So from that location and that history, we kind of like mapped it to the closest cell in that history, and then we had like this relatedness value based on which we would like measure the hazard level of the whole storm cell at each timestamp in the history. And this was kind of like obtained from an earlier study where they did some hazard approximation for these convective storms using emergency data. But here we used those ESVD reports. Then the first set of results. So this was an extra-trees model. We had some like things that we didn't do correctly here. For example, because of taking those max and min values, we had clearly collinear variables, which can be seen here in the importances. For example, Z values and the accumulated rain rate values have really low importance because those are most likely correlated. And then also, I think at this point, we still didn't realize certain problems that we had with the way we were computing the hazard levels. More on that soon. But either way, we had like this way of mapping these to like these classes, these hazard levels that we computed earlier. So these essentially thresholds that are shown on the right top. So the moderate is essentially the class 1, and severe is class 2, and extreme is class 3 in the confusion matrix. And the moderate class was 10% of the hazards that had like a larger than 0 hazard, and severe was 50 percentile and extreme was 75 percentile. Yeah, and I think the problem here was that we did the wrong cross-validation here. We didn't have the time series cross-validation, and because we had like this certain formula here, we violated kind of like the independence of those observations that we were trying to predict, and that's why the results seemed good. We got a lot of 0 values here in the confusion matrix, but yeah, then we realized this when I was testing this the explainable boosting machine. And this is really interesting model in that sense that it does these trees in a different way than extreme boosting, like extra trees model. So what it does is essentially like split trees first by each variable. So it does small trees for say age and area of the cell, and then computes the gradient, builds another tree first always computing first for the age and then for the area. And then because you have like coefficients for those trees and several trees, you can kind of like reformulate the tree in that sense that you will build one tree only using the coefficient and the trees that use the data from the age, and another tree only using those data and coefficients, or like trees and coefficients that are from the for the other variable. And then you would get this kind of like proper mapping of how the model actually sees the data for each variable. And also you can like have interaction terms. So for example, here the accumulated trade rate is here and the age on top of it. So what I realized when I was fitting this, that okay, the model gets better and better when I have more leaves in the model. So it seems like I was overfitting really like well, and I didn't get any penalties from that. So it turned out, okay, I had like somehow dependent data set, and I realized, oh no, these values were dependent in time. But yeah, then kind of like we fixed that so that from each development of the cell, we only sampled one cell and then trained the model, so that kind of like we were able to still use our data. And we also used the time series split, so always predicting the next year in the cross-validation. And we got like still good results in some sense, but still the same problem was there, that because the zero class was so high, and possibly because some of the reports were not visible in our data set, or the severity of those kind of like stunts affected our results possibly. We got these really high values for the predicted class 0 in the true label. And also like an important thing that we did also was that we used smooth to balance the classes with respect to 0 class and the class that had more than 0 class values. So it helped a little bit. But this was kind of like our model. Possibly these values are because the 0 class was higher, and also like there are survival bias in the data set of the hazard, the ESPD data. Then that's enough for the machine learning model. Now here is something about the how we, or one way how we evaluated the Nowcasting procedure. So this is essentially because we got like these ellipses that dim further in time. So we had like this probability model for those. We used these kind of reliability diagrams to evaluate how well this worked. So essentially what a reliability diagram does is that it takes the forecast probabilities into certain bins and then compares those probabilities to the values that correspond to those observed or in that bin to the values that were having this probability but were observed the way they were observed. So essentially in this image here on the right, the values on that certain contour that represents the probability under that area, the values that are inside the cell are values that are, okay, we detected this, and the values that are outside the cell in that contour are kind of like no values. And those probabilities should match the forecast probability in that bin. So essentially there should be like at point 0.2 if the model is calibrated well in the reliability diagram, you should have 0.2 offset relative frequency. So 0.2 of the values should have a detected storm cell inside it. And from these results, you can see that we are kind of like under predicting at 60 minutes quite a lot, but it's not, well, it's more drastic in the higher probabilities than in the lower probabilities. And then at 2 hour mark, we have more kind of like higher probability when we offset less, as the line is totally calibrated model. So kind of like we got these results. But this is something that might be useful if you want to validate these kind of probabilistic models. Then about the workshops, well, we asked from the end users what did they think about our models, were they easy to understand. I help our consortium to essentially translate these EDERA workshop videos that we had for training these end users in Finnish. And that was kind of like the work that I did in these workshops. The feedback mostly was like kind of like, okay, these models should be fireman friendly, so they don't have time to think about, is this good or bad result. They should have really clear instruction. This is yellow because this is yellow. It has moderate danger or moderate hazard level, and that's why you should take action or not to take action. And they gave us feedback that, okay, for example, the black color here, which represented no data at that point, was really like misleading, and these kinds of things that we further like down the line fixed. And they gave us also like estimates that, okay, this kind of field would be useful in their work. So we were more trusting that we are actually doing something that they can use. And in some sense, this work still continues in the follow-up project. So those nowcasts that I showed you earlier, where there was this moving field, that's from the follow-up project where we're kind of like using CNN as convolutional neural networks to do this nowcasting and then the impact nowcasting from there on out. But yeah, to the summary. So kind of like as a take-home message, when you're thinking about weather forecasting, different time and space scales are like relevant for different use cases. The impact nowcast is about what the weather will cause. So the model that I showed, essentially those ellipses would tell you where would there be these similar hazards that were like in the ESVD data set. And we developed these models to support the rescue officials or civil protection officials and officials in hydrological agencies. And relevant things when you're doing anything is assumptions. We had to look into those several times. The data set, we couldn't do too much necessarily later on, but still we managed, and the model. So, and then finally, just fitting this kind of interpretable model can teach you something that you're like missing. So it might open your eyes to some problems that are kind of hidden there. And then these are kind of like the sources for the images. And yeah, that's all I had to say.
Thanks a lot, Heikki. for this very interesting presentation. Yeah, are there any questions? Please post your questions in the chat if you have any. And yeah, my first question would be, of course, when is a model interpretable for you?
Interpretable is, I think, like when I learned this or read this book from Christopher Molnar. So Christopher Molnar distinguishes these interpretable models and explainable models in two ways. So interpretable is a model that is kind of somehow interpretable based on its inner structure. So if we go back to this like explainable boosting machine, which is kind of misleading from my definition for the distinguishing, but in here, because you have clear definition, what's the way the model thinks about the data, how it will give the score for the value that it will predict, that's very much, you can interpret these results. Well, you could also use the SHAP to kind of get some idea, but that's when you are explaining it. You don't know anything about the inner workings. You're only explaining what the model kind of thinks with another model. So kind of like these surrogate models, if you're using a surrogate model to kind of fit on top of your neural network, say, that would be very much explaining the model. But then, like, if you would, like, I think there was recently this, I think it was called Kolmogorov-Arnold networks. And there you kind of like had explicit functions on how that network would work. That was in some sense interpretable. But then again, with these interpretable models, you also want that it's human readable. Because, of course, decision tree can be really well interpretable, but if it's too large, you will never do it to like practically interpret anything.
But maybe there's one thing, this terminology, but in very practical terms. So how did it help you that this model was interpretable? You mentioned interpretable models can teach you. What did it teach you in this specific case?
So in this case, kind of like I was fitting to the dataset, which was flawed in that sense that I had the target variable that I was predicting. So the hazard level was not independent. And how I noticed it through this interpretability of this model, of this explainable boosting machine, was through that it made all the time certain variables that I had contained into the analysis really kind of like overfit. So I think at that point I had like the location of the cell also there. And I noticed that, okay, this goes all the time, like more coarse this fit. So it clearly was getting more nuanced in respect to the data set. And it was giving good results. And then it didn't care about kind of like this side that if I increased it even more, it wouldn't get any better because it was already using all the kind of like the branches of the tree, so to say. So from there, I noticed, okay, yeah, I have this problem and I should do something about it. So this is, I think this is a really cool tool, this explainable boosting machine, because like it kind of like gives you these plots that are for the age here. for all the variables that are in the model and also the interaction terms.
Okay, yeah, thanks a lot again. Are there any other questions or comments? There's one question. Does the scope of the research include designing optimized architecture for neural networks?
Optimized in that sense that does this mean okay, so is this optimized in that sense that we did hyperparameter optimization, or optimized in that sense that it's fast to use? We didn't do the fast to use side.
Both. So the structure of the neural network affects the accuracy, the statistical properties, and the computational properties.
So like in the sense that we just fit here the model so that we would get some output, and we did the hyperparameter optimization as well. But in terms of the efficiency in any other way, I don't think we did anything else on top of that. So if there is something kind of like over there, then we didn't. At least I don't know what would have been the thing on top of that.
But you're also using more and more transformer networks, or is this not so dominant yet in your applications?
Well, in my applications, kind of like I can show you the network that I'm using here. So, or the result from the. So over here, this is from a follow-up project where we're using a certain type of convolutional neural network. It could be like that, kind of like these transformers could be in some way useful in some problems, but with this data set, which is essentially the opera radar composite, there is this rule for, or statistical kind of like, I guess, theorem that things nearby are more related than things further away. And I feel like that's because like transformers takes things like kind of like, if you have, say, an image, say a cat image, you would take the image of a like tail and image of the ears and so on. But with the weather radar, because like you're having data further away from the radar, so the things here on the south or on the bottom of the image, they are not related too much like explicitly to those values that are high up in the north. So in that sense, using transformers over certain other convolutional neural networks, kind of like transformers do not support this kind of data set because of that, like things nearby are more related than things far away. Spatial statistic rule.
Yeah, I mean, that's the basic idea of all machine learning, I would say. Similar inputs should result in similar outputs. But the question is, what is similarity? So similar in the sense of being nearby in time, in space, or being nearby in terms of statistical distributions. Yeah, this is a very broad principle. Yeah, maybe I move on to another question. There was a question besides SHAP values. Did you also use other explainability techniques, or is SHAP more or less the dominant explainability technique?
So over here we didn't use SHAP at all. So we only used kind of like the importance scores from the scikit-learn version of the extra trees model, and then like also the explainable boosting machine, which kind of like gives these plots. So like, well, yeah, they kind of like do these were the only things that we used.
So these are not SHAP values that we see here.
Here are no Shapley values. So
I see.
these are like the proper definitions. Like in this image that I'm showing, these are the proper definitions how the model does decisions. How it's like the coefficients from a linear regression.
Okay, thanks for the clarification. Then another question, do you have tools for detecting when you are going out of distribution or the distribution is shifting? As in with climate change, won't the future storms look very different from the current and past ones?
Yes, that's a good question. Of course, our model is quite simple. So in that sense, kind of like because we're looking at what is happening now and what is happening in the following 2 to 3 hours, the distribution is already more or less there. But that's a relevant question in that sense that will this work in future models, or do you need to train it again? I think like eventually you should train it again, because I don't have that kind of out of distribution way to measure it. But yeah, kind of like still, like even though there is climate change, the problem I think in kind of like if you would say do this kind of like convolutional neural network here, it's not that problematic necessarily, because before that your radar network will already have changed and you would have a problem because of that. But on top of that, the fluid dynamics still are more or less the same on that location. Was the temperature different or not? But of course, like if the gradients would have been higher, then like these things would matter. So I guess it kind of like depends on the application you are using this, because like I'm concentrated on the following 2 hours in my work. It's very different from the kind of like the physics and modeling that you need to take into account if you do something in the order of days, weeks, months, or years. But yeah, it's hard to say like whether these like future storms will how they will change, like in that sense.
Okay. Yeah, thanks a lot again, Heikki.
Yeah, thank you for everyone for questions, and thank you, Alex, as well.
Yes, then, yeah, have a nice weekend. Bye.
Yeah, bye.